For this lecture, we're going to talk a little bit more about cation exchange capacity and hopefully give you some visual references for how this might look in the soil. So first of all, remember what a cation is. It's an element with a net positive charge. So in terms of the soil, what we're talking in terms of cations are usually, remember we've got our four basic cations, which are calcium, magnesium, sodium, and potassium. But there's also aluminum, which is a +3. There's iron, which is usually a 2 or a 3+. There's hydrogen, which is a 1+. There's ammonium, which is a 1+. And there are other potential cations in the soil. And there's lots of them. I mean, it could be everything from tin to manganese to copper. And a lot of these are also plant nutrients that the plant is going to use for its life cycle. So remember the sources for the cation exchange complex. We've got clay particles that they obtain their charge from isomorphic substitution. There's also iron and aluminum oxides, fairly rare around here, but in tropical and humid soils these are common. Organic matter is a huge driver in cation exchange, and all this cation exchange results in a net negative charge. So it comes from broken edges, it comes from substitutions, from isomorphic substitution, and then there's also this idea of charge density. And charge density is related to, all the clays have a net negative charge, but not all the clays are charged equally. If you remember back to that table where we showed the cation exchange capacity of vermiculite compared to kaolinite, compared to smectites and organic matter, you can remember that those are quite different based on their charge density. So here's, think of it like this. We've got organic matter, we've got clay particles, and each one of those has a specific number of, or a specific amount of negative charge associated with it. And with every negative charge, an equivalent positive charge can therefore occupy that particle's charge. And remember, it's balanced. If we've got something that has 7 or 8 negative charges, the soil is always going to have 7 or 8 positive charges balancing that out. There's not an extra negative charge hanging around making these soils electromagnetic. So remember that with cation exchange, this is happening at the surface of the clay. And so generally what happens is there tends to be a concentration gradient. And what I mean by that is as you move away from the colloid surface into the bulk soil solution, the concentration of nutrients tends to go down. Now that happens on a very, very small scale. It's not something you can necessarily see. But remember that the concentration of nutrients tends to be higher near the soil particle and lower out in the bulk solution. And these things are in equilibrium. And what that means is that if a plant pulls up nutrients from the soil surface, that the cations in the bulk soil solution will replace the elements taken up from the soil surface, and those things have to remain in equilibrium. Again, if not, then we're left with positive or negative charges hanging around in the soil that don't have a partner. And if this happens, it kind of disrupts the equilibrium, but it usually doesn't happen. And so remember that the exchange occurs on the soil colloid, and that the soil solution then provides replacement for those those cations that are pulled up from the soil, the soil colloid surface. So if you were to look at this on a soil solution scale for a clay organic compound, if you look on the left, you'll notice that we've got 1, 2, 3, 4, 5 negative charges, and then associated with those 5 charges are a calcium, a magnesium, and a sodium. the sum of those charges is 1, 2, 3, 4, and 5. So those 5 negative charges are occupied by those 5 equivalent positive charges. Now, that doesn't mean that exchange cannot occur. And so if you've got aluminum, potassium, and hydrogen out in the bulk soil solution, those can exchange and kick the other elements off of the exchange site because there's an equivalent amount. So this is just an example of how exchange can occur in the soil. And so there's a few things that drive this. Number one, we've talked about this, is plant uptake. If nutrients are removed from the soil, we've got this exchange that occurs to replace nutrients that are pulled up. And then also, if we add nutrient to the bulk soil solution, if there's a lot of that nutrient in the bulk soil solution, it can then kick off different elements from that clay surface or organic matter surface and replace them. There's a few things that you need to consider too. Soil drying is one of the things that causes nutrients to detach from the particle surface. And also chemicals additions, we already talked about that. This is like fertilizer additions. Those two things can either add to or deplete the amount of nutrient on the exchange site. And the exchange site is kind of a storehouse for plant nutrients. So it's good to have this exchange. It makes nutrients so that they're not mixing up with other nutrients or being leached out of the soil profile. And it's kind of it's kind of a storehouse for these nutrients that the plants can use. And so if you're to visualize the storehouse in the soil, think of all these different, these particles are obviously blown up a lot here. They're actually very small, as you'll recall, but they're kind of a storehouse for all these different nutrients. Most of these here are plant nutrients. The ones that are not are aluminum, sodium, and hydrogen is a plant nutrient, but usually not in the sense of the plant roots pulling it up. And so anyway, these positive charged ions are plant nutrients. They're stored in the soil and the plant does have access to them. So there are certain preferences for the exchange site, and it's related to the charge on the cation. So we showed the example of aluminum. If you look right here, this is what we call a lyotropic series, and it tells you kind of the preference for the exchange site for different cations. And the order goes: aluminum first is about the same as iron, and then calcium, potassium, ammonium, and sodium. So that means that the exchange site, all other things being equal, if you have an equivalent amount of calcium and an equivalent amount of aluminum, the exchange site is going to prefer that aluminum over the calcium because it has a higher cationic charge. Okay, and in fact, we are going to see this in lab on Friday. I'm going to show you an experiment that I've got set up that shows you that with these different cations, there is absolutely a preferential treatment for aluminum, and where sodium is almost excluded. So anyway, basically in a nutshell, what this is telling you is that the cation exchange site is going to favor certain elements over others, and it's related to that charge. And also within that charge, it's related to the charge density. You'll notice that the potassium and sodium have the same charge, but why is potassium more favored than sodium? And the reason being is that the charge density on sodium is much less than potassium, and so it means that the sodium element, it has a larger surface area, and potassium has a smaller surface area. So if they have the same charge over different surface areas, it's easier for the potassium to exchange or to be adhered to the soil or the clay surface. than sodium. And so if you were to look at this on an individual element level, on an individual clay level, what can happen is you'll have a clay particle here, and you can have several others, and depending on how much charge is available, you'll have aluminums on there, you'll have irons on there, sodiums, hydrogens, and so forth. And as those things come off, then other elements will take their place on the exchange site. Okay, and again, it relates to these different chemical preferences. It has to do with the charge. It has to do with another thing that we call the hydrated radius, and I'll explain more about that in lab on Friday. Sodium's kind of unique in that it has a fairly large hole of water, which is kind of a film of water around the element. And because of that, it's got a fairly large film of water around it. It doesn't like to adhere to the clay surfaces nearly as much as like an aluminum. And so that leads to a condition which we have talked about before, but is called dispersion, whereas aluminum and calcium cause what we call flocculation. In other words, the different clay particles tend to coagulate and flocculate and form larger particles. They're individual particles still, but they kind of coagulate and join together. And so that does it for this lecture, and that does it for cation exchange capacity. Next, we're going to be moving on to another soil chemical property, which is soil pH, and that'll be very interesting.